So this is an example of the application of the branch and bound method for the knapsack problem. So let's suppose that we have this instance of the problem with 4 items, each with the corresponding weight listed on the table and the corresponding value too. We have already computed the value density, which is the division of the value by the weight. So, for instance, item 1 weighs 4 kilograms, the cost is 40 units, and the value density is then 10, and so on. I wrote here the formula that we use in order to make our decisions and some data to start the process. So, of course, at the beginning, we haven't chosen still anything. So the first node in our tree is going to be here. And this is for object 0. I mean, we are just starting the process. And I will be writing to the right the 3 values that we need to be computing all the time. At the beginning, I will also use the names of the variables to make it easier for us to remember. So if we start with the first iteration, of course, the weight that we have taken is 0. The value of what we have taken is still 0. And the upper bound is going to be the value, which is going to be 0 plus the weight that we are interested in carrying, which is 10, minus the weight that we have already taken, which is 0, multiplied by the density, the best density that we can find, which is actually the 10 for the first item. So that gives us a value of 100 as the upper bound. Then we start picking or not the objects to be stored on the knapsack. So let's start with object 1, of course, and let's suppose that here it means we take object 1 and there we do not take object 1. I will write a note here. So this is for object 1. Okay, so if we take object 1, it means that now the weight W is going to be 4 because we are putting object 1 into the knapsack. The value of what is contained on the knapsack is 40 because we are taking object 1, and the upper bound is going to be the best we can do with the remaining objects. And this is going to be computed in the following way. So it's going to be the value plus the total weight, which is 10, minus the weight that we have already on the knapsack, which is 4, multiplied by the best. Since in this case my table is already ordered from the largest to the smallest value density, it is very easy to see that that is going to be the 6, meaning that this is going to be 40 plus 6 times 6, which is 36, plus 40. This will give us 76 units. Now, let's see what happens if we do not take the object 1. Then, in this case, W is still 0. We haven't taken anything. Value on the knapsack is also 0 for the same reason. But in this case, the upper bound is going to be the value, which is 0, plus the total weight on the knapsack minus what we have already taken, which is 0, multiplied by the best density without object 1 because we decided not to take it. So that would be 6. And the result of this is, of course, 60. And then we continue exploring things and we go to the next level where we are considering, I will abbreviate it like object 2. And in this case, we do not pick object 2. If we pick object 2, then the weight is going to be what we have, 4, plus the weight of object 2, which is 7. So that means 11. And we don't even need to complete the rest of the computations. Why? Well, because we are violating the constraint of the weight of the knapsack. So if I take object 1 and object 2, the weight in the knapsack will be 11, which is larger than the 10 we can take. So I will stop searching on this branch of the tree. But I can continue exploring the rest of the open leaves, right? So in the case that I decide not to take object 2, the weight will be still 4, the value will be still 40, but the upper bound now is going to change because, of course, we are considering the 40 we have plus the 10 minus the 4 we have. But now the best I can do will be choosing the next value density on the table, which is value 5 for object 3, and that will be 40 plus 6, 30, 70. All right. And what happens now? You see that from the open branches to explore or to expand now, I have 2. One, which is this one. I can try here, or I can try here. But we need to choose the best one. And the best is the one with the highest value, which is, of course, the 70. So I will, of course, choose that one. And here we will, as usual, have 2 possibilities. Picking or not, in this case, object 3. You can see, of course, that for each level, we are talking about one of the objects on my list. So I don't really need to put this label, but it's just to make it clear now in the explanation. I don't know what I am doing here. There we go. All right. So if I take object 3, W is gonna be what we had, 4, plus the weight of object 3, which is 5. So that gives us 9. value is going to be the 40 that I have plus the value of the third object, which is 25, and that gives us 65. Very good. And what about the upper bound? Upper bound is going to be what we have, which is what we have in value, which is now 65 plus 10 minus 9 multiplied by the best density that we have, that in this case is 4, the last item in my table, and this will give us 69. Okay. And what if I don't choose object 3? If I don't choose object 3, then my weight is going to be still 4. My value will be 4. And the upper bound is going to be the 40 I have plus 10 minus 10 minus 4 multiplied by 4, which is the density value for the next item. And that gives us 6 times 4, 24, 64. Okay. So now we have 3 open nodes to explore, or branches. The one that is still there with that color, this one, and this one. And from those, the one with the largest value is going to be the 69. So we can see that by choosing this one, we can continue exploring. I will do something like this to allow me to write the numbers. So in this case, of course, we choose object 4. We do not choose object 4. I'm sorry that it is getting cluttered here, but I think that you can still see. So if I choose object 4, it means that W is going to be the 9 I had plus 3, and that gives 12 as the weight. And this is larger than the amount that is allowed in the knapsack. So I cannot continue exploring this node for that reason. And from the ones, let me see if I can erase just the arrow, because the eraser here is kind of big. So we still have these possibilities, right? I don't know why I forgot this one. So these are the ones that we have. But you can see that 60 is smaller than 69. So this is not going to happen. 64 is smaller than 69, so this is not going to happen. So my solution would be this one. And we can, I made a mistake. Yeah, I made a mistake. I forgot to do a computation. It will not change the result, but let me correct it in order to avoid doing the whole video again. So, because I forgot to compute here, because of these cluttered numbers. So, in this node, this one here, we chose not to take object 4. So, the weight will be 9, of course. The value would be 65, I'm sorry. And the upper bound will be 65 because there are no more items to take. So this is going to be the value in this node, and the comparison that I was doing in order to decide whether I can continue still exploring or not is the same. I mean, 60 is clearly smaller than 65. So I don't need to do this. This is the best I can expect if somehow I continue doing things on this branch. And the best I can expect of this other node is 64. And 64 is smaller than 65. So it's not attractive. I won't continue exploring that if I still had more items, right? And so that means that the only branch or node left is this one, which is going to be actually the optimal solution. Meaning that the knapsack is going to contain object 1, not the object 2. I mean, I am just traversing the tree. So this is node object 1, not the object 2. Yes to object 3, not to object 4. So basically, I am just adding 2 of the items to the knapsack, and I am getting the best value I can do. So I am trying object 1 and object 3. So the value that I am getting is 65, and the weight I am putting into the knapsack is 9. That's it. I hope you enjoy it.